So we have talked about carbon capture and sequestration in many ways now, in different perspectives. This is another nice opinion article in Nature that just came out that I found worthy of including here. It gives you the caveats of the race to recycle carbon dioxide. So recycled carbon dioxide is a little bit different than carbon capture and sequestration. Capture and sequestration is something that's going to put it away for a long time, hopefully geologic time scales, whereas recycling is basically trying to capture and produce other products that need carbon dioxide, so-called carbon utilization. And there is always a debate about whether this is going to really work and whether this will really take out carbon dioxide from the system or just displace it. For example, the formation of syngas using carbon dioxide captured at some industry and mixing with H2O to produce a kind of a synthetic gas that serves as a fuel and can use many other different feedstocks is argued to be one of the utilization of CO2. But then it's argued that the CO2 has to be at a very high concentration in the capture or it'll take energy to concentrate CO2, and often producing H2 and other things that are needed to mix to be mixed also end up taking up energy. So and the products that are produced by carbon utilization are then sent off somewhere where that carbon dioxide emission from those products is not tracked even when there is a life cycle analysis done. So it's often referred to as displacement. So you just move carbon from one box to another rather than taking it out of the system and putting it away for a long enough time. So all kinds of details exist in the arguments. Parts of a chemical plant here in Tongizhen, China, that will recycle about 160,000 tons of CO2 into fuel each year. So considering we are emitting upward of 30 and 40 billion tons of CO2 or CO2 equivalent, this is a very tiny fraction, but the argument is that this is going to scale up somehow, and of course the counter argument is that we don't know whether they will scale up and whether they'll be carbon neutral and so on and so forth. So here is some schematic of reusing carbon dioxide. Companies are turning the greenhouse gas into many products. Some products lock CO2 away for decades, but others are short-lived solutions, so the gas quickly ends up back in the atmosphere. So you are not really putting it away, and it's still very much in the system, but you just displaced it in time. The sources of CO2 here in some products come from the fossil fuel fed power plants. In others it comes directly from or indirectly through the plants from the atmosphere. So from industrial and power plant emissions and from the atmosphere. So there is the capture stage and the reuse stage, and we have to look at the life time of the sequestration involved. So if you take it from industrial and power plant emissions, then the techniques involved are microalgae cultivation, chemical carbon capture, and then the reuse part can produce syngas. So fermentation by microbes is one way, but that can also be fed from syngas, or you have catalyst assisted electrochemical or chemical conversion, and this is a very energy intensive process as well. So energy consumption involved and the net CO2 that is actually being taken out of the system, at least for a short period, has to be tracked with life cycle analysis kind of calculations. So all these can feed syngas, which is a mixture of CO and H2, fermentation by microbes, and all can produce fuels like methanol, ethanol, and methane, or they can provide feedstock chemicals for methanol, formic acid, and so on. And the step from here can also directly go to produce polymers, which are maybe longer living sequestrations of decades, but the argument argument made is that it's much better to take directly from the atmospheres through direct air capture. But then the argument is there is that we are not yet ready to, or we don't yet have processes of direct air capture that are scalable. The largest one that was installed in Iceland last year only takes out about 800 cars per year off the road, I think, something like that. So you have to always see how much CO2 is actually being taken out in these direct air capture systems and whether they're able to scale up to meet the global warming targets that we've been talking about. Nonetheless, these tend to inject into building materials through mineralization, calcium carbonate, for example. So they can put it away for a long time and is argued to be one of the better ways of doing it. Trees and plants are obviously naturally doing it, but some crops can be converted into fuel. Like BECCS, bioenergy and carbon capture and sequestration, and there are chemical conversion of CO2 into fuels of feedstock. Fuels or feedstock chemicals often requires hydrogen, as we are seeing here, from the industrial waste gases or from electrolysis of water. Okay, so direct use without any conversion of the CO2 theoretically can go into enriching air and greenhouse gases to increasing plant yield, and we have talked just in another podcast that in fact the carbon fertilization has been working even through the Pleistocene. Injected underground to help recover oil, so this so-called enhanced recovery, pumping CO2 and enhanced oil recovery doesn't really sequester it, plus it pumps out more oil, which is more CO2. So you have to be careful about what that means. Nonetheless, looking at the lifetime in terms of how long CO2 is locked up in reused product, the feedstock chemicals only put it away for months to decades. Polymers can store it for decades. Buildings and building materials like concrete can put it away for months to centuries, depending on how they are coated and protected from leaching out CO2 again. Enriched air can work for days to years, so if you have carbon fertilized forest, it can put away carbon for years, but there are other details there as well. And of course, injecting underground can be years to centuries. So this is the argument. Carbon dioxide can be pumped into concrete where it can be stored for many years instead of putting into products which may belch it out again in much shorter time. This paper talks about how life cycle analysis was done for the more biotech approaches to taking away carbon dioxide. So overview of our three-pronged approach for pathway, strain, and process optimization. Overview of applied tools and strategies to advance acetone and isopropyl alcohol production from waste gases from a proof of concept to industrial level. So acetone and IPA are basically solvents for other industrial production processes. So pathway optimization, there is genome mining, engineered enzymes, which at least I feel have a lot of potential for the future, and combinatorial library. I'm not going to go into the details. Strain optimization, which gives you the rate of reactions needed by the enzymes that will scale up the processes to industrial. Process optimization, fermentation development, and scale up. So life cycle analysis is done. Again, it's not end-to-end in the sense that even if you do it for carbon capture and utilization part, the carbon re-released in the utilization process is not accounted for here. So this is the life cycle analysis. I won't go into the details. So these are the current production routes from fossil fuels. So coal gasification for syngas, producing with methanol synthesis into methanol, methanol to propane, and then to phenol, acetone, IPA that we talked about, oil, natural gas, and production from waste carbon argues to take it from emissions from municipal solid waste, biomass, so gasification processes and so on, gas fermentation to again produce acetone with animal feed and biogas and IPA. Okay, so there is the recycling process happening here. So this is cracking involved here and reforming involved here. So here other inputs, chemicals, utilities. So there is a system boundary, there is the outputs and the main products being acetone and IPA. So these are just steps of life cycle analysis. Okay, so I'm obviously not going into great details here. So this is the comparison of current routes of acetone and IPA and the developed gas fermentation process, starting from industrial waste gases, municipal solid waste or biomass. Steps that are particularly energy intensive or result in toxic waste are indicated by symbols. So you can see these symbols here. B is process flow diagram of Lanzatech, which is the company that is running the Chinese plant as well. Gas fermentation process that shows various inputs, outputs and process steps, as well as the system boundary used for the life cycle analysis. And the life cycle analysis compares greenhouse gas emissions, shown in black, of the traditional production processes with the gas fermentation route, where traditional routes result in greenhouse gas emissions. You can see here greenhouse gas emissions in kilogram CO2 per kg of CO2 taken up. So total emissions, processes and avoided off gas. So you can see the argument is that the waste carbon method here has negative emission. Fresh fossil and these so for acetone and IPA, both have positive emissions, whereas waste carbon has net negative, even though here you have some emissions in the process as well. So this just gives you several steps involved in carbon capture and utilization. I will have a couple of other podcasts on technical and economic feasibility of these carbon capture, utilization and sequestration methods, and also on whether they are they will be useful for meeting Paris Agreement goals in terms of global warming targets of 2 degrees C or 1.5 degrees C by 2100 with a 66% probability. Okay, so again, just a short introduction to the various issues and various processes, various claims that are involved, and some suggestions such as where CO2 sequestration can provide a longer term removal from the system, like putting into concrete. Of course, there is the geologic sequestration as well, and enhanced oil recovery. But as we said, enhanced oil recovery pumps CO2 in but brings out oil, which is going to burn and produce more CO2. So overall, whether these methods serve to reduce total emissions or give us comfort, saying anyway we're going to take it out of the system, so let's keep burning oil or doing other things that emit CO2. So lots of issues involved there. Okay, but I will leave this here.